Hello viewers, in today's class we are going to discuss one important definite integral, right? So here we have to evaluate this integral which is from 0 to 1 x raised to cos a minus 1 divided by log of x, right? And here this a belongs to the set of real numbers provided that a is not equal to the odd multiple of pi, right? So this is an important condition over here, that this a belongs to the set of real numbers, but a is not equal to the odd multiple of pi, right? So let us start and let us see how we can easily integrate this function, right, from 0 to 1. So here we are not going to use the routine method or the normal method of integration here. Rather we'll take the method of differentiating an integral under the integral sign, right? So here we'll use the method of differentiation under the integral sign, right? So for this, what we will do, we'll assume this integral as I of a, right? So we'll take this integral as a function of a, right? So I of a can be written as 0 to 1 x raised to cos of a minus 1 divided by log of x dx, right? So now what we will do, we'll differentiate both sides with respect to a, right? So here we can also say that we'll take the partial derivative of this function with respect to a, right? So what we will do, we'll write it like this: di over dA, and the derivative sign or the operator d by dA will differentiate this function with respect to a, right? So what we will write, d over dA of x raised to cos a minus 1 divided by log of x, right? Now here what we have to notice is that here we are not going to differentiate this function with respect to x, so x will be treated as a constant over here and the variable is a, right? So we can take we can write this expression as I prime of a, and now we can write 0 to a, and we can take 1 over log x outside the integral, and we have the derivative of this function with respect to a, right? So we'll write x raised to cos of a, and since 1 is a constant, so the derivative of a constant is 0, so the derivative is here 0, and so we are left with only d by dA of x raised to cos of a, right? So now here we'll separately see how to find the derivative of this function with respect to a. So we'll give it a special treatment over here. So now we have to find the derivative of this function with respect to a, right? So what we will do, we'll slightly modify this function, and we'll write it like this, that is e raised to log of x raised to cos a, right? Because this function, that is x raised to cos of a, is same as e raised to log of x raised to cos of a, because we know that e raised to log of p is equal to p, right? So we can write x raised to cos a as e raised to log of x raised to cos of a, right? So now we can write this expression as d over dA, and see we'll use the properties of log here. Log m raised to n is equal to n log m, right? So we'll take cos a in front of this log sign, so we have e raised to cos of a, and we have log of x, right? So now we have to differentiate this function, which is an exponential function, right? So e raised to cos a log x being treated as a constant, right? So we have the derivative of this function as e raised to cos of a log of x, and then by chain rule we'll differentiate this function with respect to a, right? That is cos a log of x, right? So now e raised to cos a log x is equal to x raised to cos a. So here we have x raised to cos a, and here log x is a constant, so we'll take it outside this derivative operation. So we have a log of x, and the derivative of cos a is minus of sin a, right? So now the derivative of x raised to cos a with respect to a is given by this expression. So now we have I prime of a as 0 to 1 over log of x, and for this expression we have x raised to cos of a, we have log of x, and then we have minus sine of a, and here we have dx, right? So we see that log x and log x get cancelled, so we are left with, we can take this negative sign outside, so we have minus 0 to 1, and then we have x raised to cos of a sine a dx, right? And now if we closely examine this integral, we see that now we have the function of x here, so sine a would be treated as a constant, so we can take it outside the integral sign, so we have minus sine a, and we have 0 to 1, and x raised to cos of a dx, right? So now we have I prime of a is equal to minus sine a, integral from 0 to 1 x raised to cos a dx, right? So now in order to evaluate this integral, we'll make use of this result, that is x raised to n dx is equal to x raised to n plus 1 over n plus 1, right? Because cos a can be treated as n, right? So we have I prime of a is equal to minus sine a, and we have here x raised to cos a, so this is x raised to cos a plus 1 divided by cos of a plus 1, right? And the limits are from 0 to 1, and here we have taken n as cos of a, right? Now substituting the limits here and taking the difference, we have minus sine a, we can take 1 plus cos a outside, so we have 1 plus cos a, and when we take here 1 raised to cos a plus 1, this is simply 1, and when we take x is equal to 0, 0 raised to cos a plus 1, that is 0, right? So now we are left with I prime of a is equal to minus sine a divided by 1 plus cos of a, right? So now we have arrived at this result, and when we see this result, we see that this is a differential equation in the variable a, right? So I prime of a is dia over dA, and we have minus sine a over 1 plus cos a, right? So now what we will do, we'll integrate both sides with respect to a. So we have d of ia over dA, and we'll integrate both sides with respect to a. So we have this expression, right? So here we have I of a, and now we see that this integral is a very simple one, because the derivative of the denominator exists in the numerator, right? Because the derivative of 1 plus cos a is negative of sin a. So such integrals can be written directly as the logarithm of the denominator, right? So we have the log of 1 plus cos of a, and here we have the constant of integration, right? So now we have the value of I of a, which is the given integral, that is equal to the logarithm of 1 plus cos of a plus c, where c is the constant of integration, right? So now here our aim is to find out the value of this constant of integration, right? So for this, what we will do, we'll take the use of this integral, that is I of a. So if we take a is equal to pi over 2, right? So if we assign this a the value pi over 2, then if we substitute this value in this integral, then what we will get, I of pi by 2 is equal to 0 to 1. Then we have x raised to cos of pi by 2, because a is pi by 2, minus 1 divided by log of x dx, right? So we'll make use of the boundary conditions here. So when a is pi by 2, we'll take this value of a over here to get the value of I of pi by 2, right? And we know that cos of pi by 2 is 0. So here we have x raised to 0 minus 1 in the numerator. X raised to 0 is 1, so 1 minus 1 is 0. So the integral disappears here. So we have I of pi by 2 is equal to 0, right? So now we have this condition, that is when a is equal to pi by 2, then I of pi by 2 is equal to 0, right? Okay, so here we have substituted this value of a, that is pi by 2, in this integral to get this result, right? Now substitute this value of a as pi by 2 in this expression. So what we will get, see, we have to find the value of the constant of integration. So we have I of pi by 2 is equal to a log of 1 plus cosine of pi by 2, right? Because a is pi by 2 and here we have plus c, right? And see, we have just calculated the value of I of pi by 2 is equal to 0. So here we have 0, and this is log of 1 plus cos pi by 2 is 0, and this is plus c. So we have 0 is equal to log of 1 plus c, and log of 1 is equal to 0. So we have 0 is equal to 0 plus c, that is c is equal to 0, right? So we have calculated the constant of integration c as 0, right? So if we now take this value of c is equal to 0 over here, see what we get. We get I of a is equal to log of 1 plus cos of a, right? And I of a is nothing but our original integral, right? So the value of this integral is equal to the logarithm of 1 plus cos a, where a is a real number except the odd multiple of pi, right? So viewers, this is how we can solve this type of problems by making use of the method, that is differentiation under the integral sign, right?